All right, so welcome to your first digital learning lesson. So this unit with analysis of functions is going to go back and review a lot of the stuff that you've learned previously, but also mixing together all the types of functions that you have learned as well. So example, we're going to look at rational functions, trig functions, exponential ones, all the ones you've learned mixed together, and then take some of them a little bit further than you may have done when you first learned them, say in Algebra 1 or Algebra 2. The first thing that we're going to look at is transformation of functions. And I want to start off by just reminding us of the basic form we use for function transformations. So we're looking at this, the parent function in this notation, we're going to assume is f of x. And so we can see that A, B, and C affect the graph in different ways. I'm going to talk about the stuff on the outside first, then we'll do the stuff on the inside. On the outside, I have this value of A. Things on the outside is going to be a vertical movement. When A is greater than 1, we're going to call that a vertical stretch. When A is less than 1, but technically also when A is greater than 0, then that's going to be a vertical compression. A can also do something else. If A is less than 0, basically if it's a negative number, then we are going to have a vertical reflection. And when I say a vertical reflection, it's going over the x-axis. Also on the outside, we have this k. This is going to be our vertical translations. When we are adding k, we're moving up by those units. Subtracting k, we are moving down by those same units. Then on the inside, things on the inside are going to be horizontal movement. And I often think of horizontal movements as kind of being opposite of what you expect them to be. So I'm going to deal with actually h first. This is going to be a horizontal translation. When h is less than 0, we are moving it to the left. And when h is greater than 0, we are moving it to the right. Do take note this is minus h, so when we are talking about when h is less than 0, it's going to look like plus h, but it's really because it's negative, and that double negative is going to make it positive. Same thing when h is positive, is x minus a positive value. So we often think about like the sign you see as it being the opposite sign. The other thing we have is b. If b is between 0 and 1, again, this is going to be opposite what we expect. This is a horizontal stretch by a factor of 1 over b. If b is greater than 1, that's actually going to be a horizontal shrink or compression by 1 over b as well. The last thing we're going to have on the inside, dealing with negatives. If we have a negative in front of the x on the inside, that's going to be a reflection over the y-axis, basically a horizontal reflection. Feel free to pause this if you want to copy those down, but I also have a much cleaner version on this side. Again, feel free to pause and copy down what you need. And so let's go ahead and look at some examples. So this handout is on the next page, but you're welcome just to kind of draw it out yourself. And what we're going to do is talk about, this is some generic function. I'm going to call it f of x, and we want to talk about what happens with each of these transformations and what that transformation is going to end up looking like. I'm going to do these first three with you. I do recommend every time I change the slide to kind of pause it, try it yourself and then unpause it to check your answer. Let's go ahead and talk about these. I see the -2 on the outside, so we know that that is going to go down by 2. When we say something is going down by 2, that means every point's going to go down by 2. So the new function, which I've called capital F of x, is going to look something like this. I move the vertices, but technically all these points are moving down by 2. So it ends up looking something like that. +1 on the inside. Again, this is technically x minus a -1. Or +1, we know this is moving it to the left by 1. So all my points are moving it to the left by 1. And then this last one, we see that there's a negative on the outside, so the points are reflected. Another way to think about this, f of x is the y, so we're basically saying -y. So every coordinate we have, the x coordinate is staying the same, but the y coordinate is changing. So this point right here, that currently is at 1, 3, its new point is going to be 1, -3. And we can do that for all of them. So this is going to become 1, -3. This is 2, -2, 3, -3. 5 is not reflecting because it's at 0. And we can see it is reflected over that x-axis. Go ahead and try these 3 on your own. Again, pause the video first, and then you can press play to get to your answers. All right, so looking at these 3 examples, D, this is 1/2 on the outside, so it's a vertical stretch by 1/2. You can also call that just a vertical compression by 1/2 as well. So that means all the y coordinates are being shrunk by 1/2. So this is at 3, now it's at 1.5. This was at 2, now it's at 1, 3, 1.5, stretching 0 is going to keep it at 0. So we can see it does look like it's been squished by a factor of 1/2. This next one, when we're reflecting it over the x-axis, definitely going off the grid, but all the y coordinates are the same. The x's are now the negatives. Like this is at x is 1, now it's when x is -1. This was when x is at 2, now we're at -2. X when -3, and then x is at -1, 2, 3, 4, 5. I'm just going to draw it on the other grid, but we can see it's been reflected over the y-axis. And then this last one, vertical stretch by 2, so everything's going to go up by 2. So this one that is at 3, and it's going to be at 6. This one will also be at 6. This will be at 4. And again, the 0 remains unchanged. Again, feel free to reach out to me if you have any questions on these or if I can explain them any better for you. Go ahead and try these on your own. Again, pause the video and then unpause it when you're ready to check your answer. All right, so in this one, -3, we see it goes going down 3. I do want us to notice that for our translations, the shape of our functions is preserved, meaning that it has the exact same shape it started with, it's just located something else. For stretches and shrinks, that of course the shape is a little bit warped and a little bit changed. And then H, we do need to remind ourselves what this means. This is asking for the inverse of f of x. And the inverse is basically going to switch our x and our y coordinates. So I don't have the original one plotted on here, so I'm going to go ahead and do that real fast. So I have my coordinates. And so for the original one, I'll go ahead and do that in black. I have at 1, 3, 3, 3, 2, 2, and 5, 0. And I want to find the inverse of it. So if I'm flipping my x and my y coordinates, 1, 3 is now going to be at 3, 1. That is what the inverse means. So if I go over by 3, up by 1, it's now located here. 2, 2, still going to be at 2, 2. Same here, 3, 3 is also still going to be at 3, 3. But 5, 0 is going to be at 0, 5. I want to make sure I connect it in that same order. So the inverse looks something like this. One fact we also know about inverses is that f of x and the inverse are going to be reflected over the line y is equal to x, which we can see. We can see that they are mirror images of each other. The second part of our notes is I just want to talk about those parent functions that we have, how we can go back and adjust them using our transformations. So I have the type of the function here, the parent function, and the transform function. We're going to do the same transformation for all of them. We're going to translate it 2 units to the left and then 5 units up. So we do need to know kind of the format for each of these. We did these in our parent function booklet. Let's go ahead and fill them in real fast. The linear function is y equals x, the quadratic, y equals x squared, the absolute value, and then the rational is y is equal to 1 over x. Could have said f of x, g of x, whatever. I'll just use y here. So we can talk about like what the transformed function looks like, and it is going to be calling the transformed function g of x. That's what I'm going to call it. So if I'm translating 2 units to the left, that is going to be adjusting our h value, and we know our h value would be -2. And then we have our k value, which would be 5. That's a vertical one. So when I go ahead and write g of x, I'm going to have g of x is equal to x minus a -2 on the inside and a +2 on the outside. The quadratic, I have x minus a -2 on the inside +5 on the outside. Absolute value, x minus a -2 on the inside +5 on the outside. And then same thing for the rational. For the rational, the inside of it is going to be considered the denominator. So I have 1 over x minus a -2 on the inside plus a 5 on the outside. The only one we can really simplify is this linear one, which is going to be x plus 7. Those are equivalent. Technically, you could also simplify the quadratic by foiling this out and then adding 5 to the constant, but you would kind of lose the transformations that you can see. So I'm going to end this video at this point for you to go back and review your notes, and then once you kind of review it, go and play the second video you see. We'll finish up the table with an exponential, logarithmic, and then trig example, and then I have one more set of examples to look at.